and then we stop before shock puller. So this is what I plan to start with today. Any questions on what we have discussed so far, or should I go ahead? No questions? Okay, fine. So let us start with shock puller. So till now we have covered some basic aspects of oblique shock. What is an oblique shock and how it is similar or different with the normal shock. Basically, till what we have discussed so far, we can say that oblique shock is a more general treatment, and normal shock we can approximate a special case of oblique shock where the angle becomes 90 degree. Okay, and we have used different relations for normal shock and derived oblique shock relation from that. So this is what we have done so far. Now let us look at shock puller. This is basically a way to represent velocity vectors for a shock. How do I represent or graphically discuss or analyze a oblique shock? So let me get a pointer. So shock puller is basically a graphical representation, okay, of oblique shock solutions. What happens behind the shock, okay, downstream of shock. So basically, when we talk about physical plane, this is what we have been seeing so far. That flow is coming at an angle to the shock, then it gets deflected, and these are our conditions 1 and 2. So this is what you see in physical plane. Let me just draw it. So this is what physically you see or observe. So this is, let us say, y-axis and x-axis, right? So in Cartesian coordinates, we absorb or we analyze this oblique shock. This, I hope everyone is clear with what are the different velocity components and what angles we have already discussed. Now, a more compact notation could be in what we call as shock puller. So instead of drawing this in a physical plane, we can draw this in a hodograph plane. Okay, now what is the difference? Here the axis is not x and y, here the axis is vx and vy. They are basically oriented along those directions only, but we basically use them to scale. So your first coordinate is vx. Okay, so let us say we orient the shock in such a way that we are talking about, we say that the incoming flow, or let us go to the previous picture. Let me take that picture. Okay. So this is how we generally represent shock. So if I draw, let me put that picture here so it will be easy for you to understand and compare. Why am I not able to select? Anyway, let's see how much has been copied. Okay, fine. This is fine for our purpose. So if you look at this image, right? So you see that if I orient my shock in such a way that this is horizontal, V1 is horizontal. Okay, so I can say that this is Vx and Vx1 is V1 because I have oriented in such a way, right? I have oriented the shock in such a way that it becomes horizontal. So I can say that this is my point A. Point A, you can say that this is the incoming, or point A or point B, like that. So point A is before the shock. This is, let me write it for you. Let us say for this side of shock, I say this is A and this side is part B or vector B, right? Now here you see that A is drawn here, which is equal to Vx1, and for the second part I will say I will have both x and y velocities, right? So I will have Vy2 and Vx2, and this is at an angle theta. So now this shows your B, or the resultant velocity resultant behind the shock. Okay, so let me just remove this. So this is called photograph plane. Okay. So point A represents flow field ahead of the shock, marked in region 1, and point B is behind the shock in region 2. Now what is the use or what is the advantage of this type of representation? So basically what we can do is I can observe that what happens if you change your angle. Okay, let us say I have a deflection angle of theta 1 and we have the resultant components, the resultant velocity vector is coming to be at B. Okay, now let us say if I change that angle theta, okay, if I increase that angle. So what it means that you are increasing the deflection. If you increase the deflection, the shock will become stronger, right? And the velocity V2 will decrease because shock is stronger. You will have a lesser. This magnitude will be lower than V2. Okay, so for such point, let us say I write the I start with theta 1. If I increase it to theta 2, I get a resultant velocity vector at C. So if you can measure, you can see that this length of this vector C will be less than what of that of B. And this is the theta that it is. And if I create a locus of such points, that what are the possible solutions? Okay, let us say that I have a shock and then I start calculating, or let us say vary theta from 0 to theta max. Okay, basically it will give you all possible velocity combinations, velocity and theta combinations that are possible behind the shock. Okay, so that will create a locus of these points. This is called shock polar. This polar, what you are looking, this curve basically what you are looking at. If you see what I am tracing through this pointer, this is called shock polar, and any point on this will give you a solution for that particular shock, and it will give you theta and vector. So that is the use of shock polar, or representing a shock in a photographic plane. So we will look into some examples also that may make it more clear. Okay. Now how else we can modify this? So we know that flow processes across a shock, these are generally assumed to be adiabatic. We assume that there is no heat transfer, heat loss or heat gain. Okay, because it happens in a very short length and time. And A star, the characteristic velocity at the throat is the same in upstream and downstream because we have a constant area duct. So A star is actually a very useful property. I think I also talked about some clarification which I will send you. So we can use A star to non-dimensionalize. Okay, so instead of writing U and V, I can write V by A star, Vx by A star. So basically it becomes non-dimensional. So once it becomes non-dimensional, what will happen if you flow for a choking condition where Mach number is 1. So where Mach number is 1, it will be here, this circle. Your V by X, A will become 1. So this is the advantage that you will have this is called basically sonic circle. Okay, so any point which is inside, for example E or C, these are all inside the sonic circle. So these points are, these velocities, they have subsonic velocity. Okay, and whatever points are outside the sonic circle, let us say B, A, these are outside sonic circle. So what it will be? Supersonic, right? Now can anyone tell me which one will have a strong shock and which one will have a weak shock? Can you tell me from looking at this figure?
Sir, C have strong shock and D have weak shock.
Correct. So whenever the flow becomes subsonic after the shock, it is called strong shock. So C, D, E, these points have strong shock. These solutions have strong shock. And when your result is B, it means that the flow is still supersonic. So it is a weak shock. Okay, good. Now, what is the advantage? Why should I use M star? So basically, as we have seen previously, when M Mach number goes to infinity, M star goes to 2.45. So that makes our graph more compact and more usable. So this we have discussed. Fine. Moving on. So this is the relation where you can relate your M star with Vx and Vy. And we can also draw, last slide you have seen, for a circle is there for M is equal to 1. If we take different values of M, let us say 2, 3, 4, this is the different ways in which we can draw. So you see, it is not forming a circle, it is forming sort of a oval elongated shape. But you'll get circle for Mach number is equal to 1, and you will also get circle for Mach number is equal to infinity. Okay, and this is how it will look in a orthographic plane where you have non-dimensionalized using A star. Okay, we will anyway look at some numericals. So you will see how exactly we plot those points and how do we use a hodograph or shock puller to solve for any numerical. Okay, now let us talk about supersonic flow over a wedge. So it is basically analogous to when you have a pointed, what is one of your topics? So pointed projectile. So pointed projectile is basically, you can say, you take this and revolve. Okay, make a 3D revolution. Then it will have a similar feature or same type of behavior that will see. So for a solid boundary, we can say that any sorry, for an inviscid flow, where you say that viscosity is 0, we can say that any streamline can be regarded as a solid boundary. Okay, so we have already discussed that how to use oblique shock relations for flow over a compression corner. Now what we can do is, for any given values of incoming flow is m1 and theta is the angle of this solid wall. Okay, so basically what we are saying is that instead of looking at this solid wall as a separate topic, what we can say is that we have an oblique shock and we have given m1 and theta. We can look at the shock tables and find the value of m2 and b using oblique shock relations or charts. So basically we have also table like this. So we can use this table to find out resultant m2 or beta for this supersonic flow over a wedge. So this basically what we are assuming is that this is a streamline. Okay, and the flow is diverted like this. So it could result because of shock. If you don't have any wall, just the shock is inclined at an angle and it will tilt your flow, and that could also result if you actually have a physical boundary which deflects the flow. So the basic concepts will be the same, and you can here also you can use this oblique shock relations. Okay, moving on. So the basic assumption here, what we are assuming here is that the flow is inviscid. Okay, if your flow is viscous, or you need to consider viscous effects, then this assumption is not valid. Okay, but generally for supersonic flow, if you are not very much interested in what happens very near to the boundary, inviscid is a very good assumption. Okay, it works well for solid walls, solid surfaces. Okay, now another interesting thing is if you look at these two images, so what you can see is that this one is symmetrical, right? On if you take this line along the x-axis, these upper and lower angles are same. So if you solve for one, you have the result for this one also. But this one is not symmetric. Okay, there are different angles. So what we understand, or the background theory we have, according to it, it makes no difference. What we can do is we can assume this to be independent. Okay, so I can say that I will take this half plane, I will talk about this particular shock, and I will solve for it using whatever, either you use the equations or tables, or you can also use the holographic plane. So I will solve for this M2. Now if I want to solve for this M2 dash, I need not consider this. I will take this bottom half plane, and then I will say that this is M1 velocity is coming, M1 is the Mach number, sorry, M1 Mach number is the incoming flow, beta 1 and theta 1 are given, and I want to find M2 dash. So this, for calculation of M2 dash, you need not bother what is the flow conditions here. These are, if this is shock is attached, then these two shocks are independent. They will not interfere, or while doing analysis, you need not consider both of them together. You can consider them to be independent. Okay. Now for such a flow, if your theta decreases, suppose you have a very small angle, okay, and let us say in a limit, if we take theta to 0, now what about beta? Will beta will also go to 0? No. Beta will go to a limiting value of mu. And basically what we have studied previously, mu is denoting your Mach waves. So this is the relation we had. If you assume that theta is going to 0 in the limiting case, basically it is a very small, infinitesimally small angle, then beta will go to mu, and if you put this limit in this equation, you will get that m1 sin square square m1 sin square mu will be equal to 1. Okay, or in other words, I can say that mu is sine inverse of 1 by m1. So this is called Mach angle Mach number relation, and this is how it will look. So if theta is, let us say, 0, then we have Mach wave, and we can use mu is equal to this, and we can solve. That is the limiting case when theta goes to 0. I have some animations, I think they're not working properly. Anyway, so now for this condition, what we have in the last slide. So what about pressure, temperature and density? What happened to them? So these are the relations what we have obtained for oblique shock. Previously we have derived all this equation. Now in all these three equations, I will just substitute m1 sin square beta to be equal to 1. Okay, so if for example if you take this equation, you put m1 sin square beta to be 1, it will become gamma plus 1 divided by gamma minus 1. This is 1, gamma minus 1 plus 2. So what it will be? Gamma minus 1 plus 2. It means gamma plus 1. So numerator is gamma plus 1, denominator is gamma minus 1, it becomes 1. Similarly, if you look at this equation, if you substitute m1 square sin square beta minus 1 is equal to 0, this whole term will become 0, this will be 0, and it will be 1. Similarly here, m1 sin square beta minus 1 is equal to 0, it means this term will be vanish and will have 1. So what do we see here is that density, pressure and temperature ratios all are 1. So if your ratio is 1, what is the delta? What is the change across that shock wave or Mach wave? So the change is then 0 because they are the same, right? So if rho 2 is equal to rho 1, delta rho is 0. Similarly, delta P is 0 and delta T is 0. So what we see is that the limiting case, when we are it is not for shock, it is for Mach waves. So when we are talking about Mach wave, we say that all the flow properties, pressure, temperature and density, that become 0. Okay, so but there is a very small, infinitesimally small change, or we can say that there is no finite change across this shock, across the Mach wave. There is no finite change. Okay, finite disturbance in the flow, and we see an infinitesimal change. That is how we define Mach wave. And when we are talking about this point P, let me go to the last slide. So we are talking about point P. We talk about how the flow properties change across wave which was having at point P. Now, because of that, we can say that point P could be any point in the flow field. That is how we generally represent Mach waves. Any point in the flow field, the flow across that point is basically having the no or infinitesimally small disturbance. There is no strong density or pressure jump like we see for a normal shock. Okay, now let us have some comments. So the lines what we have discussed in the last slide. So these are called, they will be at angle mu, and these are called Mach lines or Mach waves. Okay. So Mach waves are basically the weakest isotropic waves that are possible in a supersonic flow field, and the delta, what we looked into the last slide, the delta or the change will be only very small, infinitesimally small or negligible change. Okay, it will not have a strong step changes that we see for a shock, but it will be very small. It will be hardly discernible. That sort of change will be there. Okay, the Mach number also does not change. Mach number almost remains constant. And okay, so there is a difference. Mach waves, they do not change, but if you have Mach line, okay, these are also weak asymptotic waves, but it will cause some finite changes to the properties of flow passing through them. Okay, in a uniform supersonic flow, Mach wave and Mach lines are linear and inclined, so both are having the same angle, but in non-uniform supersonic flow, where Mach number is varying, it is not constant throughout a flow field, but it is varying from 1 to. So mu, because mu is sine inverse of this, so it will also vary with Mach number, and the flow Mach lines will be curved. Okay. Now, if you look at the flow field, so there are two lines. Okay, it could be mu in this direction or in this direction. Okay, it could go up or down, and they intersect in a streamline. So if this is your streamline, then you have two solutions, positive and negative. So basically what you can say is, if you rotate it or revolve it, it will form a conical surface with vertex at P. Okay. Now this is for 3D. 3D it will have a conical surface, but if you are looking at 2D, it will have two lines. Right? If you cut a 3D body by a plane, it will have two lines which are called which are basically denoted by positive and negative directions. Okay, so basically if you are standing here, if you are looking towards the flow direction, then positive sign is right side of you, near your right hand, and negative sign will be at the left hand. Okay, now this Mach lines will introduce infinitesimal but finite change. Okay, there will be some change in flow properties when flow passes through them, and these are affected. These lines are basically referred to as characteristics. Okay, so there are some more. Let us talk about this. So Mach waves are, as I said, they are weak isentropic. So isentropic is assumption which is fairly good. So we can say that Mach waves are weak isentropic waves across which there are infinitesimally or insignificant change in flow properties. Okay, expansion waves are also isentropic waves, but they introduce finite property change. Okay, once the flow passes through them, they have small but finite change of properties. Mach waves are the weakest. Okay, they are the weakest wave that you see in isentropic flow, and limiting zero strength that a flow cross will not experience any change in property. Whereas Mach line is also weak, but it will cause a finite change. So that is the difference. It will be almost zero change, but this is has Mach line has some change to the flow properties passing through it. Okay. Okay. Anyway, so we will discuss more about characteristic lines and Mach waves in the next class. Let us stop for here for today.